Okay, we're going to finish up chapter 30. I'm going to combine, 31. 31.4, 31.6, and 31.7. Kind of skip and pick a little bit, but that's okay. We need to get this idea, though, of what's going on. So, what I want to start with is kind of leave off what we said last time. Maxwell's equations basically adding the displacement current to Ampere's law really put it all together. And from that, Maxwell was basically able to say, okay, we figured out everything we need to figure out about electricity magnetism. From a classical perspective, these 5 equations, if you add the Lorentz force law, basically tell everything there is classically, we say classically, from this perspective. It explains everything about electric fields and magnetic fields. It explains all the way they do stuff. They haven't come up with anything extra outside of this in what we call a classical perspective. That's pretty amazing. And Maxwell, one, was able to see this, and then two, see displacement current, and then see, hey, we figured it all out. This is everything together. And this was darn cool at the time. And less than 100 years, the argument was made, we figured out electricity and magnetism, and of applying from Newton's optics was more ray tracing. Really from the early 1800s to the middle late 1800s, we figured it out. When really from Alexander Volta all the way up to Maxwell. It was crazy. They figured it out. So let's just go back just a little bit. Maxwell's equations, as we said, it's Gauss's law. I'm not going to rewrite these. We wrote them last class. Gauss's law for magnetism. Faraday's law that was changing, of course, magnetic fields produce electric fields, and Ampere-Maxwell law. Which said changing electric fields and current itself creates a magnetic field. And they also add in the Lorentz force law, which you've seen. I just hadn't really put it together. And that is that the electrical force from these electric fields, I would say force from the electric and magnetic fields, because when you got one change and the other one shows up. So if you got electric fields in general, you got magnetic fields, even though you don't really notice it unless there's a little static combination. It's going to be equal to Q times E, if you remember, plus, if you remember, V cross V. And the book pulls the Q out. I'm going to leave it together. And we just took the electric force and magnetic force and put those two equations together. And we got the Lorentz force law there. This is the culmination, these 5 equations are the culmination of standard electrical theory. The book says, and I can read the book, Gauss's law, charged particles create electric field. Faraday's law, electric fields create magnetic fields. Gauss's law for magnetism, there's no isolated magnetic poles, no magnetic monopoles. The electric fields have to come back on themselves. If you got north, you got south. We think now there may be, some people claim to have magnetic monopoles seen. I'm not there yet on it. Maybe some weird obtuse situation. Ampere Maxwell's law is that currents create magnetic fields and changing electric fields create magnetic fields. And of course, Lorentz force law, electric fields cause forces on charges, and when you take into account a charge moving in a magnetic field, there's a force on it as well. Fundamental laws of electromagnetism. It is that. The book goes into some kind of digging deep a little bit between it. I do want to look at properties. I ended the last time, and this is 31.6 properties of, E-M stands for electromagnetic waves. Electromagnetic waves. What if you had a changing electric field? Well, a changing electric field creates a magnetic field. Well, what if that magnetic field keeps changing at the same time? It creates an electric field. So if you have a situation where you've got a changing electric and a magnetic field, and if it just so happens, the way the system's set up from the geometry, if that occurs, what happens? Can that happen? And of course the answer is yes. That's what we know that light is nowadays. And radiation, when you think of radiation from UV radiation, infrared radiation, to X-rays and stuff like that, radio waves, microwaves and stuff, is all that. In that situation, Maxwell said, all right, there's a few properties of these things. One of the properties is they form sinusoidal waves. They form sinusoidal waves. These things do. And these waves are independent of charges or currents. They just can occur in space itself. Wow. As long as you've got a field and these waves are just field oscillations moving through space itself. Let me write that down. These waves are field oscillations. I want to say electric and magnetic field oscillations moving through space itself. And remember, we can create, as long as you've got a changing electric field, you can have a magnetic field. As long as you've got a changing magnetic field, you can get an electric field. You don't have to have a current for there to be an electric field. You don't have to have a current loop for there to be a magnetic field. You just got to have a field. You just got to have a field. So these sinusoidal waves are independent of charges that would cause electric fields or currents that would cause magnetic fields. They're transverse waves. So the oscillation of the electric field is going to be perpendicular to the direction of motion. Remember, transverse, perpendicular to the direction of motion. Of course, compression waves are the amplitude changes in the direction of motion. And the electric field and the B field are perpendicular to each other. So if you want to think of it, this is the electric field, this is magnetic field. If you have the electric field doing this, well, you can have then a magnetic field doing this as well. So they end up going like this. Oh, I gotta get this right. I'm having trouble. So what I'm going to do is do this and try to do this. So they're going to do this. And that's the way they oscillate. The magnetic field here and the electric field here are perpendicular to each other. They're transverse. So the direction of motion must therefore be what? In that direction. So they move like this, going forward. What they're doing the other way, they're oscillating in a direction perpendicular to the direction of motion. Okay. And let's just say that the E cross B, if we do a cross product, remember perpendicularity? When things are perpendicular, that's what the cross products we use. And so remember, it gives a vector out. Now if these two are perpendicular, perpendicular to each other in the direction of motion. V. And I can say V is perpendicular to both E and B. Sometimes known as a pointing vector. It's interesting, called pointing, P-O-Y-N-T-I-N-G. And actually, you could argue points in the direction that the electromagnetic field goes. Excuse me, the electromagnetic wave goes. And then the velocity in free space, in a vacuum, which we talked a little bit about the other day, this velocity is equal to 1 over the square root mu naught epsilon naught, and that's 3, the 1 centimeter, 3 times 10 to the 8 meters per second, which is, of course, the speed of light. And, of course, then Einstein used this to help with special theory. And the last one is, and this relates to electric field magnitudes and magnetic field magnitudes. The last one is the electric field magnitude is going to be equal to C, which is the speed here. They use C for the speed light. E equals mc squared, imp. If you saw the movie Young Einstein a long time ago. C, 3 times 10 to the 8th, times the magnetic field equals the electric field strength. So which one's much, much stronger? Of course, the electric field. In an electromagnetic wave, magnetic field times 3 times 10 to the 8 equals electric field. So it's 10 to the 8. So that's like 100 million times smaller. So the magnetic effect we get from light is much less than the electric field. I think I did 8 inches there. All right. So when we think of light, we tend to think of it as electric field. It does have magnetic field properties, but those are fairly weak. And it would take really strong magnetic fields to make those effective. Be shown. Can you bend light with a magnetic field? Yeah. It's hard to do so. Okay. All right. Electric fields. So when you think of electromagnetic wave, think of the electric field, an oscillating electric field up and down like this, moving that way. And so you can think of that in space. So in space, space actually is being modulated itself due to this electric field. That's what fields do. They modulate, they change space. It's crazy stuff. Now, the book goes into, some more stuff, pressure and radiation, pointing vector stuff. I'm not going to get into that. A little bit on antenna theory. My gosh, antenna theories. That's tough. That's some tough stuff. I'm ham certified, and I understand antenna theory a little bit, but those guys that can do antennas, they've got this concept of fields down. That's pretty crazy stuff. That's what I want you to know with this. I do want to talk about polarization. We'll do talk about polarization. The book gets into this before it gets into light itself. I've done some work with polarizers and polarization back when I worked at Livermore. You can use polarization to measure stress in objects, how much an object is stressed. In other words, how much there's some internal twisting on something. And Let's look at what polarization is. And polarization is 31.7. So when you think of polarization, the classic way of doing it is I take two polarizers. Polarizer. Let me get it to the camera. Polarizer. Other polarizer. If I take one and I place them like this, you can still see through it. You can see through the polarizer a little bit, right? You can see through it. Then you go, well, that's nice and everything, and then I come back here and I look at this and I stick the polarizers together. You can't see through it at all. You can't do it. You don't see anything through there. Now, how can it be in one case you can see through things, and then in another case you can't? That's cray-cray. What's going on? Well, if I hold this, keep the one in the front still, and I rotate this, I'll rotate the one in the front. That looks like magic. Of course, you all know what Isaac Asimov said about magic. Any technology sufficiently above what somebody understands is magic. But here, all right, you can see through it. Right about there, you can't. And what we found is every 90 degrees, you can see through it really good if you have two polarizers together. And if you have two at 90 degrees, at another 90 degree rotation, you don't see anything. So what's going on? What the heck's a polarizer, first of all? What happens when something is polarized? And then, how's it useful like this? Well, we say something's polarized. When you think of polarization, we're in a polarized political environment. The two camps were polarized. That means you would normally think opposite direction. Got Democrats, Republicans. Their ideas are polar opposites, we would say to each other. Because you think of the poles, North Pole, South Pole. They're completely opposite ends of the world. Well, when we think of light being polarized, how could light is think of an electromagnetic wave. When we think of an electromagnetic wave there, if it's polarized, what's completely different for this? Well, it would be this direction. Because if I'm oscillating in this direction in the electric field, that's completely different from anything in this direction in the electric field. Because if I'm at an angle, I got a little bit in the y direction, a little bit in x. If I'm doing like this. So I got a little bit in x, a little bit in y. But if I'm doing straight up or straight across oscillation, those polarizations, the direction of the oscillation of the field is completely independent of each other. So when you think light is polarized, it's when the electric field vector oscillates in one particular plane or direction, we can say. A lot of times we'll say, this is vertically polarized. This would be horizontally polarized. So that's the electric field. Now, what happens is, can you make light oscillate in one direction? Well, light can be naturally polarized. Glare is a good example. Glare. I'll say reflections from a pond, lake, or even the road. The road acts as a mirror to some extent. You can see it if you look way out sometimes on a road, you can see like things in the, what's that thing doing in the roadway out there? On a long, flat road, you can see. And what happens is it's just reflections, or just say reflections. It is reflections. A light from, say, something up here hits the ground, comes up, and you see it. And it reflects what we call grazing incidence there. It acts like if there's water on the road, you see it more of a thing. But glare and reflection and polarized sunglasses get rid of this when you're driving. It's one of the good things. Let's talk about what they can use for glare, of course, and fishing glasses. Your fishing glasses that you use on ponds to see the fish and everything, they get rid of the glare from the pond or the lake. So let's think lights oscillating, it's just random. It's just, a lot of times light itself, the light wave travels will have random polar. It may just be this way, or it may be rotating over time. It can be doing like this over time. It's called circular polarization. Or it can be, there's lots of different ways of doing that. So now let's just say it's rotating here at this angle. So light hits the board. And so part of the light that tries to go into the board, like that, well, the board will absorb that polarization angle somewhat. But the light that hits, the component of the light that's going up and down, it just kind of bounces off. It doesn't get absorbed as much, because here the electric field's actually trying to go into the material. If it's hitting like this, it tends to want to go off, so it reflects. So after it does this, part of the light that's polarization in and out of the board gets absorbed. Some of it does, a lot of it. It depends. And it comes off, so the light coming out here may be predominantly vertically polarized. You have some that's not, but you have a lot of it that is. And it doesn't have to be a mirrored surface or something as flat as this. Over a long distance, you can actually have, I've seen cinder block walls do this, especially if they're painted decently enough, so they're not that porous. You don't show the porosity of it. And that's kind of cool. It does it. Lakes do the same thing, except when light hits it, it's coming up this direction. Because light hits the pond, ones that are going into the pond or into the lake tend to be absorbed more. Ones that are going this way aren't. Okay? Now, if you use those same fishing glasses for try to look at glare on the side of a building or the side of this board, would it get rid of the glare? The answer is no. Because fishing glasses, those polarizers, are meant to absorb light in this direction and transmit vertical direction. Now, if you wore a pair of fishing glasses on your head like this, it would look kind of weird. But if you did, then you could get rid of the glare on the side. You wouldn't see it. You see very little glare there. This glare is a polarization effect. And if you're wearing those glasses, if you wear polarized glasses, lots of times you'll see it light on certain, you'll see kind of a pattern on glass and stuff, on car glasses, because of the way that it's a laminate type glass material as part of the manufacturing process. And you actually can see some of the, sometimes polarization angles are absorbed more than others, let's just say. There's some things going on there. Polarization works like that. It causes this glare stuff. Now, what I showed you was two polarizers. Now, what the heck is a polarizer? Well, Polaroid, the company Polaroid. The guy, basically what he did, I can get into the details, but you don't care about it. But bottom line, he created these long chains of polymers, I think, in one direction, like fence posts, fence going down. And they tended to absorb light in one direction. These crystals did. I don't know if they were polymers or not. They may have been. But these crystals, or this material in one direction, and it lined up, and they tend to line up. You would actually kind of pull on it and get them to stretch in that direction. So as they would stretch in that direction more, light would go through, and it would absorb most of the component of the light oscillating vertically, let's say, if assuming it was, the chains were vertically. And it would let through the ones that were going this way. So the molecules would be here, and it would let through the light that was oscillating back and forth. That component of that vector. So polarizers, you can think of it as, kind of directional filters, maybe, if you want to think for the electric field. And they work, we get pretty darn good polarization. Now, they do absorb some light in general. They're not, nothing's 100% perfect. I mean, they do absorb light a little bit in the other direction. But in general, they mainly absorb light, say in this case, oscillating vertically. So now I've got light going through this one that's only oscillating horizontal. What if I take my next polarizer and line it up so the polymer chains, those chains of material, are horizontal? It's going to absorb all the light in that direction. So this absorbs a component of the electric field vector here. This one does. This one now absorbs a component of electric field going horizontal. I've absorbed vertical polarization and horizontal polarization. Have I got any light electric field components left? The answer is no. So in that situation, get it just dead on. You don't see anything through the polarizer. You don't see anything through there. And that's one of the things how polarizers work. Now, polarizers, there is actually something called Malus law, and I'll show you here in a minute. That will define the light that goes through here, the intensity of the light that comes through here. Malus law, now put it in terms of intensity. I'll put it in terms of intensity.